Hello, I'm Miro again, and this will be the last lecture in the biofuel series. Lecture 1, Simple Biofuels. Biogas upgrades, utilization and landfill gas. We will finish the biofuel recording with this section. Again, an overview of the biogas process. Please look at the previous section and we will repeat simply what happens when we produce biogas. Organic residues, any kind, or purpose-grown crops, any kind of fresh organic material, can be mixed and digested, pre-treated if necessary, sterilized if necessary, and digested typically for the industrial applications, 37 degrees, 20-25 days retention time. This is the digestion tank. The sludge is a wonderful fertilizer, and it's brought back to the fields as fertilizer to replace artificial fertilizers. The digested material can be stored intermediately at the next intermediate storage tank, which also emits biogas, can also be collected. The biogas itself, as a final product from the system, can be either used directly or cleaned, upgraded, and used in common engines or in any advanced way. This is how the actual system would look like. Again, cattle manure or any additional resource being pre-treated, mixed, homogenized, then brought to the biogas digester, which needs to be heated to maintain the proper temperature, generally 37 degrees, constant. The outflow brought back to the post-fermentation tank. So you usually see 2 tanks out there in the field, which is also kept at the proper temperature to use the last possible emission of gas being produced inside and collected definitely. And then the residue being stored and then used somehow as fertilizer, while the gas can either be used directly in a CHP process, let's say an engine that is adapted to work with the acid-containing raw gas. Not only acid-containing, but also only half of it is a combustible material, that is methane, while the other half is CO2. Or processed and then utilized or sent out, either injected in a natural gas grid or used as automotive fuel. And you can see these buses all over Sweden, actually in all of the big cities. You can also tank cars in Sweden. Sweden is mostly using its biogas as transportation fuel, which is actually the best case, the best alternative you can choose. While in other countries, for example Germany, you would mostly see the gas being utilized directly at the spot for electricity production and heat, or upgraded and sent to the natural gas grid. Biogas can also be produced from sewage sludge. It is again organic material. It's not much of a biogas that is being produced. As a rule of thumb, every human being, that's you and me, right, produces sewage that goes to the sewage treatment works, which ends up in a sewage sludge after the sewage has been treated. And the sewage sludge itself can be converted to biogas, can be digested. Generally, approximately 10 normal cubic meters per year per person can be produced as biogas. This is not much. 10 normal cubic meters of pure methane, if we take it so, is like 1 liter of gasoline. Sorry, 10 liters of gasoline. It's not much, but if we talk about multi-million cities, this is a considerable resource. And if we talk about the worldwide potential, which has not been used to its full extent now, definitely, it is a very, very serious resource. This is just one example. One of the sewage treatment works in Stockholm. This is the first one that started producing biogas, and the process is being optimized more and more. All of the sewage treatment works in Stockholm now are producing biogas. If we utilize biogas as fuel in common engines, we will have to upgrade it. First of all, to get rid of the acidic gases, scrub away mostly the hydrogen sulfide and anything else that can damage the engine. This can be done by several processes. The most common one would be physical absorption. You just dilute these acids in water. In most cases, this is quite easy to do. And then take the water out of the system while you have clean gas coming out. Any other acidic scrubbing processes can also be used. Dry oxidation, oxidize this thing into, well, water and sulfur dioxide, and then treat the sulfur dioxide in the common way. Adsorption on surfaces, liquid phase oxidation or cryogenic method has been touted as very promising for the near future. The next stage of the upgrading process is to scrub away the CO2. This might be a bit more difficult even if CO2 is not directly detrimental or damaging for the hardware of an energy conversion system. Still, you might want to upgrade the biogas to almost pure methane. Otherwise, you have a low-quality fuel. CO2 scrubbing can be done again with physical absorption, using the fact that actually CO2, that is carbon dioxide, is soluble in water much more than methane, 1,000 times more. So if you treat the gas at high pressures, the raw biogas at high pressures, in a water column, CO2 from the gas actually gets into the liquid water, while methane doesn't. This is the way to separate CO2 and methane from the raw gas. Some kind of chemical absorption can also be used, pretty much similar to what power plants would attempt to clean CO2 from exhaust gases. Again, adsorption on surfaces, some kind of membrane separation at high pressures or low pressures, cryogenic separation or any chemical method can also be used. The most commercial process is the purely physical absorption in water. Water treatment is at the foreground here. The typical biogas digestion tanks, first one, post-treatment tank, second one, and 2 columns for the biogas treatment. This part of the plant you can do without it if you utilize the gas directly at the spot in an engine. But if we would send it to the natural gas system or use it as fuel, you have to treat it. And upgrading part of the whole system might cost equally much as everything else. Landfill gas is also biogas. If we have a typical solid waste, municipal solid waste, or any kind of other waste containing enough organic materials, typically kitchen garbage, collected and landfilled. That is how usually municipal waste was disposed of in the past. Not anymore in many places, but it continues to be treated in this way, simply collected and buried in the ground. This is a big pile of organic material. The moment you seal it, and you have to seal it as much as possible to prevent any leakage, both towards the underground water table and up methane leaking up to the atmosphere. Sooner or later this will happen. You better collect the methane because inside anaerobic digestion will start. And the landfill gas is again a typical biogas being produced inside the landfill as soon as it reaches anaerobic conditions. This is how the gas collection system would be built. Already when the landfill is being created, certain sound pipes, collection pipes, perforated pipes simply, are put in the system, injected into the landfill. Some kind of collection system is created on top, summing up all the gas, whether being treated or not, sent to an engine or upgraded and used in the same way as common biogas. It makes sense to capture and burn the methane from a landfill, absolutely, because otherwise, sooner or later, it would leak to the atmosphere. And we have to try to prevent any kind of leakage from any kind of biogas production or landfill production process. As a rule of thumb, if 3%, only 3% of the gas leaks out, we may not save any greenhouse gas emissions, keeping in mind that the methane itself is 21 times much more potent greenhouse gas than CO2. The landfill site has a certain life cycle because it's a finite system. There is a pile of garbage being sealed. In the beginning, there is also oxygen there. Common rotting would start, and the oxygen will start to be consumed. The common rotting process using oxygen actually creates nice, warm environment inside. This initiates, now together with the fact that oxygen finishes, this initiates the anaerobic digestion. The anaerobic digestion takes over. The remaining organic material is being converted to biogas. So the biogas production, or the methane production, starts. Methane is the useful material in the biogas, of course. It accelerates for a couple of years, typically. It peaks after 5 to 10 years, typically, and then it starts fading away with a higher or lower speed, depending on how big the landfill is, what kind of material there is inside, how much organics, inorganics, if there are toxic materials, for example, that can stop the process, and so on. It usually continues up to 20, 25, even 30 years, but the gas production slowly drops down until, well, the gas is not useful anymore, or in the end it contains mostly CO2 and not methane anymore. To summarize, landfill gas is essentially anaerobic biogas. Any sealed garbage disposal site will sooner or later start producing landfill gas. And it's better actually to collect and use it rather than letting the methane escape to the atmosphere. Landfill gas and biogas can be used either directly in a CHP plant or upgraded and injected in a natural gas pipework, or combusted in common engines. Substitute natural gas is what we call the upgraded biogas used or injected directly into natural gas pipework. If we do so, or if we use it as transportation fuel, it has to be upgraded to almost pure methane. The greenhouse gas neutrality can be difficult to estimate, especially if methane leaks from the system. Very careful life cycle analysis and life cycle cost, of course, of the whole system need to be carried out, and especially the greenhouse gas win from the system or profit from the system needs to be assessed very carefully if we would be replacing, for example, a fossil fuel with methane produced from biogas anaerobic digestion. Thank you. This was the end of the biofuel lecture.